Hello, my name is Kristiina Jokinen and I'm from AI Research Center, ICE Tokyo Waterfront. Today I will talk about contextual coaching, support for well-being based on environmental sensor information and conversational AI. Here is the talk structure. I will first introduce the context-based interaction by talking about smart home environment, embodied interaction, and support for well-being. I will then continue with the details of enabling such interaction related to knowledge graphs, conversational AI, and experiments with the Furhat robot. Finally, I will conclude with future views. On environmental context, it supports our well-being and good life. So it's very important that we can talk about it using natural language and find recommendations that can help us to maintain and improve our well-being. The environmental states contain different information like temperature, humidity, CO2 level, light, etc. And we receive information about them through sensors. An important aspect in communicating about environmental state is the embodiment of communication. As Pfeiffer says, intelligent interaction requires physical instantiation, not merely the intelligence is in the abstract algorithms. Social robots share the living space with us and they have access to environmental information. So it's natural that they will also be able to talk about it, provide information and recommendations to the human partner. We assume that AI systems realized as physical robots or as simulated agents provide preferred interface for conversational interactions on daily well-being. This is not only because people are accustomed to interacting with each other, but because the mind is inseparable from the physical experience. In case of elder adults or people with special need, explorations about well-being in the smart environment would also be preferably conducted via robot interactions rather than via phone or remote control interactions. That is, enabling a talk to someone. This assumption, of course, brings in many important factors in designing human-robot interaction. For instance, social robots' dual characteristics is not only a function as a tool, but also as an agent which shows social behavior. Also, issues related to personalization of the robot are important, user preferences and cultural differences. For instance, the robot's facial structure and facial expressions and the effect on the user can be studied. And we have actually done some preliminary experiments with that using the Furhat robot. However, we'll not go into this direction in this talk. In this talk, I will focus on how the conversations on well-being and environmental issues can be implemented, combining conversational AI, knowledge graphs, and social robots, in our case, the Furhat robots. The work is based on our earlier research presented in the last year's Human-Robot Interaction Conference. We focus on support for well-being based on the environmental issues. The general framework is in the eVita project, which is a 3-year cooperation between EU and Japan. And the main objective of the project concerns prototyping virtual coaches to sustain older adults' well-being in smart living environments. Our task is to work on the coaching dialogues related to various use cases like physical exercises and cognitive exercises. And in this case, we talk about effect on environmental states. Knowledge graphs represent knowledge of the world and provide explanations of how entities are related to each other. They provide a semantic interpretation of the world and the context in which interactions can take place. Moreover, they support context-aware dialogue modeling with richer descriptions of the domain and an intuitive way to build and understand the content. Also, they can be extended and modified according to the needs of the application. For further information, I'd like to refer you to literature to check more about the knowledge graphs, graph databases, and their use in the AI research. Here you can see an example of the environmental knowledge graph in our application. It shows connections from the environmental state to various parameters. Also, various recommendations are linked to comfortable and uncomfortable states defined by the sensor measurements at a particular time. We use Rasa open source conversational AI as the dialogue engine. It allows a flexible use of different NLU pipelines and dialogue policies to enable interaction with the user. It uses state-of-the-art transformer technology and different NLU models as the default, but also allows their own components models to be included in the system. The Rasa SDK contains Action Server, which allows access to external databases. Here we can see the knowledge base actions using Rasa's in-memory knowledge base that uses the JSON database format and actions to external knowledge base, in this case Neo4j graph database. Natural language processing and machine learning processing loosely combine the state-of-the-art models and libraries to access pre-trained models and classifiers, and as mentioned, these can be replaced by custom components. The DIET dual intent and entity transformer classifier takes care of the default understanding of the user's input and recognizes both the intent and the entities of the utterance. The TED or Transformer Embedding Dialog policy predicts the next action. Other policies are rule-based policy and memoization policy that is based on predefined stories. This slide shows some user intents implemented in the system and the corresponding linguistic examples that realize their intent as a sentence. Notice that the example sentences are annotated with the concepts that are important for the knowledge-based search, like sleep disorder, humidity as an environmental state measure, etc. In this slide, we can see an example story that the system is trained on. The story is expressed using the user intents and system actions, not by actual sentences, which the sentences can be used as examples of the particular intents as shown in the previous slide. Here we can see the configuration of the system. The pipeline includes a SPACY NLP tokenizer and featureizer, and also takes advantage of several other featureizers. It uses the diode classifier with 100 epochs to track the intents and entities and to determine the system response. The dialogue manager predicts the best next action using the transformer embedded dialogue policy implemented in Rasa with 20 epochs. Let's now see a quick demo of the system implemented on the Furhat robot. The video is on virtual robot, also we also have the real robot to run the dialogues. Notice that the interaction is not optimized to dialogue interaction, but to demonstrate knowledge base and Rasa connection.
Hello, Furhat.
Hello, how can I help you?
I'd like to know what kind of environmental states are there?
The environmental states are humidity, room temperature, noise, light, air quality.
And what kind of problems are there?
The problems are high temperature, high noise, high humidity, low temperature, sleep disorder.
Okay. Can you tell me about the measurements?
The measurements are noise level, humidity level, temperature level, CO2 level, air pressure level.
What do you recommend for high humidity levels?
I found this recommendation. Use dehumidifier.
And what will help when it's very noisy?
The recommendation is close window.
Okay. What do you recommend for high temperature?
I found this recommendation. Open window.
And what do you recommend for low temperature?
The recommendation is use heater.
I have a sleep disorder. What do you recommend?
I found these recommendations. Have regular lifestyle. Avoid eating late. Do exercises.
Are you really a chatbot?
I'm a Furhat robot with Rasa Conversational AI.
Thank you. Goodbye.
Goodbye. See you soon.
As for the future work, many improvements can be made. We need to increase the system functionality by extending the current knowledge base and also integrate it with other use case domains. An important step is to include dynamic knowledge of the environment, that is, to integrate real sensor data coming from the sensors in the smart home environment. This requires an extra component that coordinates and interprets the raw data into suitable classes, which represent concepts in the knowledge graph and can be used in the dialog management as values for the particular parameter slots. Other extensions are related to methodological issues, for instance, solutions related to graph embeddings to integrate knowledge graph reasoning into dialog model. An important issue is the design of dialogue strategies to support friendly, contextually appropriate dialogues between the user and the coach. We have already started experimentation with large language models and related APIs like ChatGPT, but more studies are needed to understand better the behavior of the models and, for instance, suitable prompt designs. As for the other dialogue management issues related to embodied interaction, studies on emotional and empathic interactions are relevant, as well as issues related to cultural and individual differences, as already mentioned. Finally, I want to emphasize ethical and privacy issues, which are important in the embodied human-robot interaction studies. They need to be taken into account in the complex knowledge modeling, into use of large language models, and the design of the dialogue systems as a whole. Thank you for your interest in our work. If you wish to know more, please don't hesitate to contact me at the address given. Finally, I'd like to thank all the members in the project and my colleagues for useful and inspirational discussions, and also the funders for financial support for the work. Thank you very much.